Mark Rosengarten. Welcome to
Ask Rosengarten.
Hey everybody, welcome to Ask Rosengarten. I know it's been a long time since I've done one of these shows, but when I tell you that things have been crazy, I gotta tell you they've been absolutely and utterly crazy! But I have some time today, so I've got a couple of good questions that have come to me from the internet. First questions come from Phantom4476. They are, okay, can you explain to me what is the easiest way to figure out the polar and nonpolar, including how the dipole goes? Now, I'm going to assume because you use the term dipole, you're talking about the polarity of molecules. Here are 6 examples for your demonstration pleasure. The electronegativities of the atoms are, and I'm getting these numbers from the New York State Regents reference tables. In a molecule that has 2 lines or more of symmetry, which means that the electron distribution in the molecule is evenly distributed. For example, here, where the electronegativities of the atoms on both sides of the molecule are the same, this molecule is nonpolar. There has no polarity at all. On the other hand, in this molecule here, where one end of the molecule's got a higher electronegativity than the other end, and there's only one line of symmetry, that would be a polar molecule, and the dipole moment goes towards the atom with the higher electronegativity along the single line of symmetry. A little plus on that side to show that that's the partially positive side of the molecule. Here we have nitrogen pulling unevenly in this molecule. The electrons are being distributed towards nitrogen along a single line of symmetry right here. Therefore, the dipole moment is towards nitrogen along that line of symmetry, and that end is partially positive. In water, again, one line of symmetry with the electron distribution being pulled towards the more electronegative oxygen atom. Therefore, the dipole moment goes towards the oxygen, and the opposite side is your partially positive part of the dipole. In this molecule here, we have a central atom pulling with 2.6 and 4 hydrogens pulling with 2.1. The distribution of electrons is equal on all sides being pulled in towards carbon. Therefore, there is no polarity to this molecule. To this molecule here, however, we do have electrons being pulled from the hydrogen in towards the central carbon, but on this side, we've got a chlorine with a much higher electronegativity. Therefore, the dipole moment is going to be towards that more electronegative atom. And that's how you can tell the polarity of a molecule. A molecule is polar if it's got one line of symmetry, and the dipole moment is along that line of symmetry towards the more electronegative atom. His second question is, next, I'm having a problem figuring out where these prefixes and suffixes come from and how they work. Examples: nicolic hydroxide, plumbic sulfate, ferric chloride, hexahydrate. I know hexa means 6, and chromous iodide. The prefixes come from the fact that the elements that you mentioned have more than one possible ion charge, more than one possible oxidation state. We describe oxidation states either with Roman numerals to indicate what the charge is. For example, Fe+2 is called iron 2, and Fe+3 is called iron 3 with a 3 in parentheses. However, there is a traditional system that has the following. The lowest charge is always going to get hypo, then the element name, us. Then just us for the next highest charge, ik for the next highest charge, and per ik for the highest charge of all. For example, nicolic. As you can see, nickel has 2 possible charges, +2 and +3. Now in the stock system of naming these elements, Ni+2 would be called nickel 2, and nickel +3 would be called nickel 3. But in the traditional system, we replace these with these suffixes. Usually us and ik are used if there's only 2 charges. Since nickel +2 has the lower charge, any compound with nickel +2 in it would be called Nicholas. This is the Nicholas ion. like St. Nicholas, except he doesn't bring you beakers and test tubes on Christmas. And nickel plus 3, being the higher charge, would be called nickelic. So if we have NiO, that's Nicholas oxide. Strangest name I ever heard for a child. And if we have Ni2O3, that's called nickelic oxide. And that's how the prefix system works. The next example is plumbic sulfate. As you can see, lead comes in two charges, Pb plus 2 and Pb plus 4. Now, typically these would be called lead 2 and lead 4, but in the old traditional method, it's the plumbous ion and the plumbic ion. So as you can see, the one with lower charge gets the us suffix, and the one with the higher charge gets the ic suffix. So if we have plumbic sulfate, we're talking about Pb with the higher charge, plus 4. Sulfates minus 2, and it takes two sulfates to cancel out the lead. Plumbic sulfate. Ferric chloride hexahydrate. Iron has the symbol Fe. That's because its traditional name is ferrum. Now, typically, we're going to call Fe plus 2 iron 2 and Fe plus 3 iron 3. But because, again, just like the lead, the plus 2 gets the us suffix, and the plus 3 gets the ic suffix. The one with the lower charge gets us, the one with the higher charge gets ic. So if we're dealing with ferric chloride, we're dealing with the plus 3 form of iron. Fe is plus 3, chloride is minus 1, FeCl3, and because it's a hydrate, there's water trapped inside the crystal lattice structure. This says hexahydrate. This tells us that there's 6 waters trapped inside the crystal structure. The next question is, what is the easiest way to go about figuring out the product when given the reaction? I get it sometimes and sometimes not. Must be missing something. So here's some examples. First, we're going to do Mg solid plus Cl2 gas. When you're completing reactions, the phase doesn't really matter, so I'm going to leave it out here. This is an example of a synthesis reaction. In a synthesis reaction, two elements combine together to form a compound where the metal and the nonmetal bond together. So the compound will contain magnesium and it will also contain chloride. Now what we need to do is look up the charges of the magnesium and chloride on the periodic table. Magnesium has a plus 2 charge and chloride has a minus 1 charge. So the formula is MgCl2. I want you to understand this 2 being here has nothing to do with that. Chlorine is diatomic when it's by itself. So therefore, we've now got a nice balanced reaction. But the reason there's 2 chlorines here is because magnesium's charge is plus 2. Chloride's is minus 1. So it takes 2 negative 1 ions to cancel out the positive 2 ion. Second reaction example just gives you hydrogen bromide gas and an arrow. This is a prime example of what we call a decomposition reaction. We start with a compound, and unlike synthesis where 2 elements make a compound, decomposition is the reverse of that. You take the compound and you break it back up into its original elements. Its original elements were hydrogen and bromine, both of which are diatomic when they're not in a compound. The elements that are diatomic when they're by themselves are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Brinkelhoff. If you've got any of these by themselves, then that tells you you need to make it diatomic when you write the formulas. Once we're finished writing this decomposition reaction, you'll notice we have 2 hydrogen atoms on the right side, but only 1 on the left side. So we balance it by putting a 2 in front. You can only balance by putting coefficients. You're never allowed to change the formula. We have 2 bromines on the right side. Well, now we have 2 bromines on the left side too. Putting the 2 in front of the formula doubles the number of atoms you have in the whole formula. Now we have a nice balanced reaction. Third reaction is magnesium plus zinc nitrate. This is what we call a single replacement or single displacement reaction, where we have an element, typically a metal, and it's reacted with a compound that contains a less active metal in it. And what happens is the more active metal kicks the less active metal out of the compound and takes its place. It replaces it. The magnesium takes zinc's place. So what we're going to end up with is magnesium bonded to nitrate and zinc all by itself. Now, zinc isn't a Brinkelhoff. It's not diatomic, so I'm not going to throw a 2 down there. What about the formula for magnesium nitrate? Magnesium has a +2 ion charge. Nitrate has a -1 ion charge. So since magnesium is +2 and nitrate is -1, it takes 2 nitrates to cancel out the magnesium. Don't assume that just because you have 2 nitrates on the reactant side, you're going to have 2 nitrates in the formula on the product side. What if this had been aluminum? Aluminum is +3. It would have been AlNO3, and then you would have had to balance. As it is, this reaction already balances itself. And finally, we have these 2 reactants, both of which are dissolved in water. Here's what happens. These are both ionic compounds, and ionic bonds are fairly weak. Most ionic compounds have such a weak ionic bond that all you have to do is put them in water, and the water will break the ionic bond apart. And that's what's happened here. The bond between potassium and sulfur is weak enough that water can break it. Same thing with the bond between lead and nitrate. Water can break it. But when they get put into solution, something amazing happens. One of the ions from this compound and one of the ions from this compound are going to be so attracted to each other that even water isn't going to be able to tear them apart. They're going to fly at each other from opposite sides of the beaker going, "I love you! I love you too! Will you bond with me forever?" And they come together to form what's called a precipitate. Now, how do we know which ions are going to do this? We need a solubility table for this. Now, as you can see here, potassium is a group 1 metal. And our solubility guidelines say that group 1 ions, Li, Na, etc., that includes potassium, are always soluble, no matter what they're bonded with. Now, potassium in this case is bonded with sulfur. Now, sulfide is typically insoluble, except when combined with a group 1 ion. That's why K2S is soluble. What about lead nitrate? Well, nitrates are always soluble. No exceptions to that rule. So what happens is the ions change who they're bonded with. Potassium has a +1 charge, sulfide is -2, lead is +2, and nitrate is -1. You can look these charges up on the periodic table. During these kinds of reactions, the charges don't change. The potassium and lead, well, they're not going to bond to each other. They have the same kind of charge, positive. They're going to repel each other, not attract. So K is going to look at PB and go, "I'm not bonding with you." But nitrate, aha, opposites attract. K is +1, NO3 is -1, KNO3 is the formula for your compound. And PB is going to be like, "Okay, K passed me by, it's taken over my NO3. Hey, S, let's bond." And because they're the same size charge, +2 and -2, they cancel out in a 1-to-1 ratio, PBS. So what happens is we have 2 Ks, 1 K, we put a 2 in front to balance it, 1 S, 1 S, 1 PB, 1 PB, 2 nitrates, 2 nitrates. The reaction's balanced. But which one is the precipitate? Well, remember from the table I showed you, K is always soluble, no exceptions. NO3 is always soluble, no exceptions. So this will remain dissolved in water. But remember we said that S is usually insoluble. Now K is an exception to that, but PB is not. This is a precipitate, and it will precipitate out like snow. It's very pretty. I'm really sorry it's taking so long between these videos. Like I said, things are absolutely insane right now. But I will get these videos put up as I can. As you ask the questions, these were fantastic questions. Please email me at askrosengarten@gmail.com. As soon as I can get to your question, I absolutely will. So what are you waiting for?
Ask Rosengarten!